Today I want to talk about what makes things coloured from a materials perspective. Now that's not to say that I'm accepting that colour is a physical property in the world. If you've seen any of my videos, you'll know that I think that colour is a perception. Nevertheless, objects look coloured to us in part because they reflect some wavelengths of light more strongly than others. So why is this? Now, there are many physiochemical causes of colour, of course. In fact, there's a fantastic book by Kurt Nassau called The Physics and Chemistry of Colour, with the subtitle The 15 Causes of Colour. So, for example, one way that objects emit or reflect light differentially is incandescence. If we heat up a metal, it will glow and emit light. And the spectral distribution of the light emitted depends, of course, upon how much we heat it up. This was the basis of the incandescent light bulb. And incandescent tungsten filament bulbs were used to illuminate our homes from the early 20th century until about a decade ago, when they were generally banned. So another way in which colour is produced is bioluminescence. And this is a chemical process that emits light and is used by fireflies. I don't think we have fireflies in the UK. I've never seen any, but I did see them once in a trip in New Jersey. And then we have interference effects. This is the effect of multiple thin films of material. And it's responsible for the colour that we sometimes see when, for example, oil lies on top of water, and for the colour of many butterfly wings. But even though we have all these different ways in which to produce colour, the fact is, most of the things around us are coloured because of colorants, the collective name for dyes and pigments, and most of these selectively absorb light at certain wavelengths more than others because of what we call electronic transitions. So, a quick recap. Matter consists of atoms, and we can think of an atom as a nucleus consisting of protons and neutrons, and then electrons that circulate around the nucleus. Of course, I'm simplifying things. This is Dalton's simple atomic model from 1803. A more contemporary understanding is that the electrons don't exist in any one place, but rather their location is defined by a probability distribution. So it isn't really right to think of an atom as like a solar system with the sun at the centre and the electrons like planets circulating. But for us today in this talk, Dalton's model's fine. And by the way, it is the same Dalton who first systematically explored what is referred to now as colour blindness. So colorants absorb light because an electron moves from a ground state to what is known as an excited state. Now, the difference in energy between the ground state and the excited state is a precise amount of energy. And this corresponds to a specific frequency or wavelength of light. And the electron can move from the ground state to the excited state only by absorbing that very specific amount of energy or that very specific wavelength of light. So the molecule you can see on screen now is called benzene. It's a liquid at room temperature. Each of the points on this hexagon represents a carbon atom, And the single lines represent single bonds and the double lines represent double bonds. Each carbon has four hands, as I like to call it. So each carbon atom has a spare hand and is therefore connected to a hydrogen atom. So at the corners of that hexagon, at the points, the vertices, you have carbon atoms, 6 of them. Each one has one double bond and one single bond, and each one is also connected to a hydrogen atom. So we can say that the formula is C6H6. Now, it's the electrons in the double bonds that can move from a ground state to an excited state. In the case of benzene, the gap between the ground state and the excited state is very, very large. It needs a large amount of energy, and this corresponds to quanta of radiation at about 250 nanometers. So benzene can absorb light or radiation at about 250 nanometers. This is outside of the visible spectrum and so has no effect on color. Benzene is a colorless liquid. Now here we have a much larger molecule. It's 2 benzene rings connected by 2 nitrogen atoms. This structure of 2 benzene rings connected by 2 nitrogens is called an azo structure, and it's really important. I think it's true that more than half of all commercial dyes and pigments are based on this structure. Now notice we have alternate single and double bonds. This is called conjugation, and it's very, very important because it allows the electrons in the double bonds to roam, if you like, across the whole molecule. And this decreases the gap between the ground state and the excited state. So this is a very famous dye called aniline yellow, first made in 1864. It's been used to dye textiles. It's been used as the yellow in inkjet printers. And it absorbs at 460 nanometers, that is in the blue region. So making the gap between the ground state and the excited state smaller resulted in a shift of absorption to longer wavelengths. Well, we can make the molecule larger. This molecule here, you can still see the conjugation of single and double bonds, but it means that the gap between ground state and excited state is even smaller. So absorption in this case occurs at 484 nanometers. And this dye is known as acid orange 7. Also, this dye molecule is ionic. In solution, there's a positive sodium ion and a negative ion for the rest of the molecule. And this is why the dye is referred to as an acid dye. An acid's used in the dye bath when it's used to dye wool. And fibers such as wool contain positive or cationic sites where the negative or anionic dye molecule can bind to. And then we have this really large dye structure. It's called trypan blue. And now the gap between excited state and ground state is so small that this molecule absorbs light at 607 nanometers. The point of this is that you can see that there's a relationship between chemical structure and colour. Well, if I was being pedantic, which I never am, of course, I would say that there's a relationship between chemical structure and the spectral nature of the light absorbed and reflected. But we don't have to be so pedantic all the time, do we? So the point is, colour chemists can actually design dyes and pigments to have specific colour properties. In the 1980s, I did a degree in colour chemistry at Leeds University. And in my final year as an undergraduate student in 1983, I did a dissertation with John Griffiths. He was a brilliant professor there at the time. And my dissertation was about the synthesis of some novel azo dyes. I really enjoyed it and still recall it now. But in 1983, that was the last chemistry I ever did. But before we sort of finish this short presentation, there's one more thing. So far, you might think that these dyes would simply absorb at a single wavelength. That wavelength which corresponds to the energy needed to jump the electron from the ground state to the excited state. So they just absorb a very specific wavelength. But that's not the case. Why is that? Well, the reason is that the molecules can actually rotate. The azo dyes, for example, can rotate around the azo or the nitrogen-nitrogen bond, and this can increase or decrease the energy gap between the ground state and the excited state. This allows other wavelengths to be absorbed, although with lower probability. And then each rotational state can also have different vibrational states. So it's still discrete energy levels, but in reality they're so close together and there are so many of them that it looks like a continuous light absorption curve. Of course, this is the light that is absorbed by the dye. This means that light at these wavelengths will be deficient in the light that is reflected by, for example, the textile to which the dye is applied. So you can think of the dye subtracting light, if you like, and this might help to understand why the term subtractive colour mixing is sometimes used. Hope you found that sort of interesting, and speak to you next time. Bye.